Hello, my name is Suma Park. I will present about our solid-state lithium-ion battery for electric vehicles. Lithium-ion batteries are widely used in portable electronics and electric vehicles due to their high energy density, long lifespan, and low self-discharge rate. A typical lithium-ion batteries consist of an anode, cathode, electrolyte, current collector, and external conductor, which work together to store electrical energy through the movement of electron and charge carriers within the systems. The battery operates within a voltage range where the electrochemical stability of the electrolyte is manipulated, while the anode and cathode undergo oxidation reduction reactions to produce electric energy. Researches in lithium-ion batteries has mainly focused on increasing energy density, with the three main areas of focus being voltage, capacity, and electrolytes. Among these, I believe voltage is the most critical factor. The chemical potential difference between the anode and cathode materials determine the voltage as per the nearest equations with the number of transferable electrons in denominator. Alkaline and alkaline earth metal systems such as lithium and sodium have the potential to deliver high voltages, while divalent or multivalent systems have lower voltages. Capacity is mainly influenced by the material, with interconnection systems having capacity limitations. Researchers are studying the use of lithium metal as an anode to overcome these limitations. Additionally, electrolyte research is essential to realize high energy density, as the limitations of electrolyte based on thermodynamics currently hinder the utilization of high voltage batteries. In conclusion, voltage, capacity, and electrolytes are essentially factors that must be studied and optimized to achieve high energy density in lithium-ion batteries. The use of lithium metal as anode is very useful for improving energy density because it improves the capacity per weight and per volume. Also can increase the voltage. While this method can significantly improve energy density, there are potential drawbacks. Lithium metal-based lithium-ion batteries are prone to the thermal runaway at the anode and dendritic growth on the lithium metal surface during continuous charge-discharge process. And also it is create a short circuit that directly contacts the anode and cathode. This is critical in lithium-ion batteries. To address these issues, researchers have developed a solid-state electrolyte system to replace the traditional liquid organic electrolytes. These solutions allows the advantages of lithium metal to be utilized while overcoming the stability issues of the previous system. The use of solid-state electrolyte in lithium-ion metal batteries has significant advantages, including a wide range temperature stability characteristics and reduction in the risk of ignition. These factors make it the most promising next generation battery solution, especially for electric vehicles, where stability is crucial element for mobility paradigm changes. There are four main types of solid electrolyte: sulfide, oxide, halide, and polymer electrolytes. Sulfide electrolytes are the most notable due to their unique mechanical softness, which allow for cold pressing and direct contact with active areas. Despite being solid electrolytes, Sulfide offer comparable ionic conductivity to liquid electrolytes, making them the most promising solid-state electrolyte available. In a battery, the oxidation and reduction stability of the electrolyte is essential. Continuous electrochemical reactions can lead to electrolyte depletion and increased internal resistance, ultimately leading to the battery failure. However, sulfide-based solid electrolytes have the unique feature of being unstable under oxidation or reduction conditions. It is important to understand the difference between liquid and solid electrolyte systems. In carbonate electrolyte systems like NCM, graphite, the HOMO and LUMO level are outside the stability window, resulting in chemical stability. However, in solid-state systems, sulfide electrolytes in particular are theoretically unsuitable because of their low stability window. This creates a challenge as sulfide electrolytes are chemically incompatible with cathode material. But interestingly, their low stability allow them to operate reliably under conditions battery operation. The decomposed components act as a buffer layer that prevent further electrolyte contact with active areas, thus maintaining conductivity. In summary, sulfide-based solid-state electrolytes have unique properties that make them promising for use in batteries. They offer comparable ionic conductivity to liquid electrolytes and have a have the ability to operate reliably under continuous battery operation. Sulfide-based solid-state electrolytes are made of um, anion frameworks and lithium cations. They typically use combination of phosphorus and sulfur, such as lithium thiophosphate. Uh, uh, to create the solid electrolyte, Li3PS4 is the most stable combination that has been isolated by lithium ion. However, when it is highly crystallized, the ionic conductivity is low. By adjusting it to glass type, it can research to 1 millisiemens per centimeter. Li3, Li7P3S11 has a higher ionic conductivity of 10 millisiemens per centimeter, but it is difficult to synthesize and have limitation of electrochemical instability. Li7PS6 is another type of solid electrolyte that is created by increasing the portion of Li2S, which is an azurite type or solid electrolyte. This type of solid electrolytes allow for lithium migration due to the excess lithium in the structure. However, the ionic conductivity is still not large, and introducing chlorine by by doping some of the sulfur can increase vacancies in the lithium sublattice and rapidly increase the ionic conductivity. At this point, I would like to say the ionic conductivity by itself is no longer a barrier to developing solid-state electrolyte systems. In our solid-state lithium metal batteries, the interfacial instability due to the nature of ionic conduction system by solid-solid contact is a bottleneck. Although this problem is also present in liquid systems, it is particularly challenging in our solid state batteries due to the kinetics difference arising from the different lithium-ion transport mechanism. The complexity of the interface within our solid-state battery systems also present challenges. For instance, the interface at the integrated cathode tend to void, tend to fabrication of void due to the solid-solid contact, which increase the internal resistance and affects the stability of the electrolyte contact interface. This issue is critical for on our solid-state systems, especially because an intercalation-based cathode is used and any slightly volume changes can create a void. To address interfacial instability, researchers have explored coating the surface of cathode to control the contact area between solid electrolyte and cathode. If these challenges can be overcome, our solid-state lithium metal batteries have the potential to offer non-explosive and long-range electric vehicles. Thank you for your attention.